Assalamualaikum warahmatullahi wabarakatuh and good night. So today I'm going to present about vector analysis, chapter 2. So for the introduction is what is vector analysis? Vector analysis is the study of mathematical quantities with both magnitude and direction. It is essential in fields like electromagnetism, fluid dynamics, and mechanics. In this chapter, we explore coordinate system, vector field, vector operation, and theorem that link them. So, for you to understand the vector, vector is a quantity with magnitude and direction. It is very different with the scalar. Uh, Vector represent by an arrow pointing in the direction with length proportional to magnitude. For the example is force, velocity, acceleration, and displacement. Okay, so there is two techniques for addition and subtraction of vector. Each technique have vector operation in 2D and 3D. So um, to add vector, we place, so for the first one, addition, uh, the UV. So it is method that we call head to tail edit theory. But and then you can see a parallelogram method. So for the subtraction, is reverse the second vector and add it. So for product of vector, first we got a dot product for scalar A by B. So you got AB cos theta. It is give magnitude only. So while cross product is for vector, there is A multiplied by B. So you get an AB sine theta. It is give new vector perpendicular to both. So for the orthogonal coordinate system, there is a three coordinate system. For the first one, we got a Cartesian XYZ for rectangular axis. For the number two is a cylindrical, and the number three is spherical. So, what is a differential length, area, and volume? Number one is infinitesimal measurement, such as A, D, dl. D represent to the change. Differential length for the P is differential area. C is differential volume. Uh, so it is changing depending on coordinate system used. So for the gradient of scalar field, um, you can get the gradient scalar fields formula, this one formula at the, the appendix. So it is points in the direction of maximum freeze. For the example, it can be used in gradient of temperature or potential field. And then we got a divergence of a vector field. So uh, change, it is F force or change of V represent the divergence of vector field of F, while it is measured the net outward flow from a point. So if the value is positive, it is a source, while if it negative, is a sink. Example of this formula or we use is flow to fluid from a point. So for the curl, uh, represented by change F, uh, it is measured the rotation or circulation at the point. Example, the curl is vorticized in fluid flow or magnetic field. So we got N, the Laplace Laplacian. Uh, so it is appear in equation for heat diffusion and wave. Measure how a function deviates from average of its neighbor. So for the first one, we got a Cartesian coordinate system, and then we got for the number two is a cylindrical coordinate system, and the last one is a spherical coordinate system, as you can see in this appendix. Uh, yeah, we can find it here, and then uh, divergence theorem, flux, and the divergence theorem. The divergence theorem relates the flux of a vector field through a closed surface to the divergence of the field inside the volume enclosures. This allows conversion of surface integral into a volume integral, simplifying complex calculation. So there's a formula, okay, where the change f is the divergence of the vector field f. So change of v is differential volume element. Differential A is outward pointing area vector on the surface S. For the example, it is used in fluid dynamics to calculate how much fluid is flowing out of a volume by analyzing the vector field inside it. So, line integral and Stokes theorem. Stokes theorem related the circulation of a vector around closed loop the, to the curl of the field over the surface enclosures. It is convert a line integral around a boundary into a surface integral for curl, essential in electromagnetism and fluid flow analysis, where C is closed curved loop. F represents the vector field. So change of F is the curl of F. Differential area is surface area vector. Example you can use is used to calculate the work done by a rotational field magnetic force around closed loop. So, summary of a vector analysis is vector operation like addition, dot, and cross product. Um, and then we can summarize the understanding gradient, divergence, and curl. While the third one is using coordinate system to evaluate fields. You have a Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. And the last one is fundamental theorem, divergence, and Stokes. So, we go to the chapter 3, static electric field. For the introduction to static electric field, what is the static electric field? Field, it is a field created by stationary electric charge. Importance in electrostatic and application. So for the visual, uh, positive and negative charge in charge with the field lines. Okay, so we go first for the Coulomb law. Coulomb law quantifies the electrostatic force between 2 point charges. The magnitude of the force is given is F by mu naught by Q1 Q2 per R2, where Q1 and Q2 is charges. R1 is a distance between charges. Mu naught is permittivity of free space. The force is attractive if charges are opposite, repulsive if the same direction along the straight line connecting the charges. So for the electric field intensity, E, electric field intensity is defined as the force per unit positive charge placed in the field, E, force Q naught. It is a vector quantity having a both magnitude and direction unit. Units for it is Newton per Coulomb or volts per meter, visualized by field lines. Closer line means stronger fields. Example, the field around the point charge radiates outward as the one. For electric fields to the continuous charge distribution. For real-world objects, charges are often distributed over length, areas, and over the volume. These are called line, surface, and volume charges density. To calculate the electric field at a point, we use integration across the distribution line Q per L, surface Q over area for the volume Q per V. This allows calculation of E for rods, sheets, and charges volume. 4. So, for the electricity flux density, also called electric displacement field, defined as dE, it is described how electric field lines pass through the surface. D takes into account the effect of the medium, epsilon. Unit that we can use is coulomb per square meter. It is important for understanding how material respond to electric field, especially dielectric. So, uh, the next slide is about Gauss law. Gauss law relates electric field to the net charge enclosed in a surface. E, change of area. Q, it is simplified calculation of electric field for symmetric shapes, for spheres, cylinders, and planes. The law tells us the more charges inside, the more flux flow through the space. It is especially powerful when combined with knowledge of asymmetry. So, for the electric potential is the work needed to bring a unit charge from infinity to a point in space. It is a scalar quantity, meaning it has magnitude but no direction, related to field by E negative change of V. Fields point in the direction decreasing potential. Equipotential lines show regions with equal potential always perpendicular to electric field line. The next one is potential energy of a charge. A charge has electric potential energy U in an electric field by U QV. If a charge moves through the field, it is potential energy change. Example, positive charge naturally move from high to low potential and releasing energy. Important in understanding electric circuit capacitor and electron motion. And then charge distribution and density. This topic focuses on how charge spread in space. Line charge, amount of charge per unit length, surface charge per unit area, large volume charge is unit volume. This density help us model real-world charge object necessary for applying Gauss law and calculating field from non-point charge distribution. So, for the summary of static electric field chapter overview, static electric fields are generated by stationary charge except force in other charge in space. So, for the Coulomb law, describe the force between 2 point charge decreasing with the square of the distance. So, for electric field intensity, E is the force per unit charge and is represented as a vector field. For extent charge distribution line surface volume, the electric field is calculated using integration. So for the electric flux density, D quantifies how electric flows through the surface is affected by surrounding medium. Gauss law links the net electric flux through a closed surface to the enclosed electric charge, simplifying field calculation for symmetric geometries. Electric potential is the work done to move a unit in charge of field excluding the electric fields. Potential energy is stored energy of charge in field and change field position, while the charge distribution density help describe how charge is spread in space, influencing the strength and the shape of the resulting electrical field. So, um, Coulomb's law. All right. So that's all from me. Your time to Thank you for the times for listening to my presentation.